All right, 5.7. We've been talking about derivatives of inverse trig functions. So I have shown you the two main ones. Inverse sine. We did a little imp-diff / like triangle proof kind of. I guess it wasn't really imp-diff, kind of, I guess. For inverse sine, inverse tangent, and we had left off on doing inverse secant, and then we can use these three to find the other three. Okay, so let me go back to here. I remembered we used imp-diff to solve for dy dx, and then we had set up this little triangle to figure out what the secant of y was, which secant is cosine's reciprocal, so cosine would be adjacent over hypotenuse, so secant is hypotenuse over adjacent, so it's just x. And then I mentioned how you have to wrap in absolute value bars because we can't have negative values for x. I mean, you can obviously think about it in terms of like the triangle, but there's one other thing as to why we need those. And I can't think of it. Okay. Tangent of y, I'm going to have to know the opposite side. So I could do a little pi thing. We kind of already did that though. You would get the square root. Let's see, x squared minus, oh. Don't look at that. Delete.
Already saved.
How did I do that? Oh, well, let me undo it. Let me select this. Oh, shoot. Okay, well.
Well, there's like a look at the preview.
It is what it is. Look at what
It's a
preview.
little box. Like when you were in the outside view, your little box is like, you slid the box up.
I did? Like that?
Yeah, like your box is right there. You see it on there?
No. Which box?
Well, the one that's blue right now. No. On your,
No,
I'm saying like,
if you look at the
Oh.
image, there is a box that is.
I see. Oh, I see
It's
what you're
supposed to be
saying.
an overcover.
Mm-hmm.
You might have pushed it back.
I didn't even know that was in there. Okay.
whose nose did you steal?
These are the ones we used in McGonagall. I like kind of take like what I can from there, but you guys' textbooks are so different, so half the stuff I make up too. And then sometimes, I like to make up my own problems, and then I never know if they're right or not.
Oh, well, that's great.
Okay. So the tangent of y, we have to know the opposite side, so you can do pi thing. I'm just going to call this a. You get the square root of the hypotenuse squared minus 1 squared. Okay, so tangent, opposite over adjacent would just be 1. So that ends up being x squared minus 1. So there's your derivative for secant. Now this is fine. This is what I do want you to write down, but your textbook more commonly uses arc instead of inverse. So just write the derivative of the inverse secant is that, what we just found right there. The absolute value of x times the square root of x squared minus 1 in the denominator. 1 over that. And this one, just applying chain rule. I need to write this one.
Do we need arc secant of x?
Yes, thank you. Same thing for this one. Good catch. Arc secant of u for the second one. I'll have to figure out how to get those out of there. There must have been in the other ones too.
You slid the cover. Once it the cat's out the bag or something like that.
I'm just gonna quick go back to the last one and see if that will do it.
That's mostly used for like
They're hidden.
That's mostly used for like a secret.
What if you click the 3 dot?
I think that's just like my mouse.
How you can like move it around.
Interesting. Oh, weird.
Oh, there it is.
Oh! Super weird. Okay, here's what you need to write, if you have not already. The derivative for arc or inverse secant of x is the absolute value of x to the square root x squared minus 1 in the denominator all over 1. And we have something else that we're taking the inverse secant of, we'd have to apply chain rule. du dx. There we go. Okay. So we'll try one of these pretty like easy examples, and then we'll go through the other three. Just derivatives in this lesson. We'll integrate in the next lesson, and then we're almost on chapter 5. Okay, so here I have the inverse secant of 3x minus 1. Simple question, just find the derivative. Okie doke. I know the derivative is the absolute value of x, so what I'm taking the secant of, or my argument, is 3x minus 4 times the square root of x squared minus 1. 3x minus 4. That's all in my denominator. Chain rule times the derivative of the inside, which is just 3. Okay, the only other thing I'd probably do here, obviously multiply that 3 in the numerator. 3x minus 4 we have to keep in parentheses because that could have some negative opponents. For example, if x is like 0, so we got to keep that wrapped in parentheses. If it was like x squared or something that would always come out positive, we could drop them, but in this case we can't. And then I would you might see the answer like with this multiplied out, that 3x minus 4 times 3x minus 4 minus 1. You might see that multiplied out, so let's do that quick. It won't take us long. 9x squared minus 12 minus 12 minus 24x. Oops. And then 16 minus 1, positive 16 minus 1 will give me 15. Okay. Don't need to rationalize. Isn't that nice? I love that rule in calculus. They're kind of like, hey, you proved yourself that you know how to rationalize denominators, so now we just care about you doing the calculus. Yes, sir.
Wouldn't it also really be hard to rationalize with the absolute value other than the denominator?
Yeah, it would create a lot of complications. It'd probably make it like less simplified than it looks. All right. Here are our other three. So we haven't talked about inverse cosine, inverse cotangent, or inverse cosecant. So an easy way to find these, yes, sir.
Are we recording for Delaney and Jake?
Yeah, I did. Yep, I recorded it. Thank you.
The mic's hot. It's red.
Just because no audio bug at this point.
It picks up pretty a lot. I feel like when I'm like yelling in the back, like I can hear. Yeah, I hear it like in the prime spot to talk to him. Oh, Haley, these boys.
Are we gonna finish this by Friday or on Friday?
Oh, we'll definitely finish this. We might finish this today.
And then we started another one tomorrow.
Yeah, we only have one more lesson in chapter 5.
So Friday can be a free day.
So you guys will probably have a test next week. I'm gonna make this quiz take one quiz
Like Wednesday.
to save time.
Oh, we're taking like it'd be this one plus the next one is a take home quiz. Or is
Right.
it just this one?
This one plus the next one. Yep.
The first one I'll get 100 on.
Oh, I feel like on the last take home quiz, I don't think we got hundreds across the board.
Can I check?
It's kind of hard to cheat on them because you got to show your work, and Google can't do a lot of calculus.
Huh?
Okay. Anyways. So instead of going through and like doing all those imp-diff proofs for the other ones, you could, but instead of doing that, we can use some of the trig identities. These ones are the inverse cofunction. I'm trying to think if they're like on your big cheat sheet. I know definitely the cofunction identity ones are. I don't know about the inverse ones, but anyways, you don't have to know these identities. These are just going to help us find the other three an easier way. Okay. So let's take this identity right here, and I'm just going to kind of do it off to the side here. The cosine inverse is the same as pi over 2 minus the inverse sine. All right, so we're going to differentiate this because I want to figure out what the derivative of inverse cosine is. Okay, so I'm going to differentiate this, both sides.
We want to write this in
What am I doing?
arccos.
Yeah, you can do that too. Actually, you should. I probably should do that because that's what your textbook does. Thank you. I should fix that on my notes. Okay. So I can find the derivative of my right-hand side because I know what the derivative of pi over 2 is. That's just 0, any constant. And I know what the derivative of inverse sine is. It's 1 over the square root of 1 minus x squared. That's our derivative for inverse sine. So if I have 0 minus that, you're just going to get negative square root 1 minus x squared on the bottom, 1 over that. There's your derivative for inverse cosine. The negative you can either put out in front, you could put it up here if you want to as well. Doesn't matter. All right, let's figure out cotangents next. I wonder if I click this box if they'll show up. Try in a second. All right, so we're gonna use this identity that, and again, you will never have to like prove these to me. This is just a little bit of a conceptual understanding of where these come from instead of me just throwing up these random formulas on the board and telling you to use them. Okay. So similar idea here. The derivative of pi is 0 minus, we know what the derivative of the inverse tangent is. That's that 1 over 1 plus x squared. So cotangent, its reciprocal identity would be negative 1 over 1 plus x squared. I need a tray. I need a tray here that catches where my magnet does it.
Like a gutter system.
Yeah, because 50% of the time I do drop them because I'm like playing with them, but the other 50% is like I put them back in the magnet.
What if you just put like a rug?
Ooh, that's a good idea too. Like a little catch, like a mat. That might be nice on my feet too.
Like a yoga mat now?
Yeah. Not a bad idea, Mark. What do you think? All right, last one. Cosecant. I've also, these should have, oh no, duh. We're doing arcs, so we don't need that. Sorry. I was like, I forgot to put the inverse notation. That's what the arc means. All right, this one. You can probably see where this is going. Take the derivative. Zero. And then the derivative for inverse secant, that was that one we just did, the absolute value of x times the square root x squared plus 1 or minus 1? Minus 1. What do I have in my notes? Plus 1. Minus 1. So it just ends up being negative absolute value of x. Let's click it and see if it matches. Yep. Minus 1. Okay. So, just a little proof of where those come from. Here's what you have to know. Here they are in summary. This is applying like chain rule. That's what they're saying here. Like u prime would be 1 over the square root of 1 minus x squared, chain rule times du dx, so this is another way to write it. You will only be expected to know these two. Since that's all your tests on the AP exam, that's all I'll test you on too. With the exception of maybe since the quiz is take home, I could throw some of those on there since you have access to your notes actually. Okay. So let's just try some examples. We're just straight up find the derivative and then we'll try a couple applications. Oh boy. Find the derivative of this function here. Okay, so here I see I'm going to have to use product rule. And now I can use my new derivative rule for inverse cosine. All right, let's get after it. So looking at my first term there, I would do my first term times the derivative of my second term. Power rule. Chain rule. Plus second factor times the derivative of my first factor, which is 1. Plus my derivative for cosine inverse is similar to sine, 1 minus x squared under the radical, but I have a negative 1 up top. Okay, let's simplify this a bit. So here, I have that 2 and that 1/2. I'm going to bring down that negative power and rewrite it as a radical. That takes care of this. And then it looks like I just have negative x squared on top. Here I just have plus the square root of 1 minus x squared plus negative 1 over the square root of 1 minus x squared. So I see some common denominators already. So what I'm going to do here, and obviously there's kind of different ways you could go about this, different steps, but I'm going to add these together. And then in the meantime, I'll kind of make a common denominator with this one, and then I'll add it in the end. But these two straight up, the green ones, they already have common denominator. So I could just rewrite that as negative x squared minus 1. And then here, I don't want to times the top and bottom. The square root of 1 minus x squared to make common denominators. Okay. That works out pretty nicely with my numerator as well, where I just get 1 minus x squared. And then they're ready to add together. Common denominator, square root of 1 minus x squared. So let's see, negative x squared plus negative x squared, negative 2x squared, negative 1 plus 1. Those will cancel. Here's your derivative. That was a fun problem. That was kind of cool how those came out to matching denominators. Okay. Let's try another one. Arc cosecant, which is the same as inverse cosecant, of x over 2. All right, so looking at my derivative rule for inverse cosecant. So secant and cosecant, that's the one that has the absolute value of x, but in this case we have x over 2 times the square root of x squared minus 1. Now since this one's cosecant, it's all over negative 1. Don't forget about chain rule. Times the derivative of the inside would be 1/2. Okay, a little simplifying we can do here. First of all, anytime you have a number inside of a square root, like this, if this number is obviously positive, that's the same as taking 1/2 times the absolute value of x. You can almost kind of like bring that constant out in front as long as it's positive. So I could technically rewrite this as 1/2, but I got to keep that x in the absolute value because, again, x could be a negative number. And then underneath the radical, I'd probably just write that as x squared over 4. Don't worry about minusing the 1. But then these 1/2 would cancel, so this would be a perfectly simplified answer. Again, you're probably not used to like leaving fractions within radicals because technically that's not a simplified radical, but in calculus, once we
Where did the times 1/2 come from again?
because I had x over 2 here, so I just rewrote that as 1/2 times x.
I meant the red one.
Oh, chain rule. The derivative of x over 2 is 1/2 because you have to do the derivative of the inside.
Oh.
Chain rule. Yep. Good question. You could also write that as like 1/4 x squared if you wanted to. All right, we just have one more straight up finding derivative and then 3 applications. Oh, I think we can finish this. Let's do it. Ooh, this one is, oh, look at all this going on here. All right, so I have a natural log and I have an inverse tangent. Now, I would probably expand this natural log before I find any derivatives by using like my properties of logarithm, that if I have an argument that's being divided, I can split it up into 2 different logarithms by subtracting them. So I would probably start, I'm not doing derivative yet, so I'm going to make sure to notate like I'm just kind of simplifying here. So I can't really bring this 1/2 out because this 1/2 is only being multiplied to the natural log, okay? So when I expand this, I have to make sure that both the top and the bottom are being multiplied by that 1/2. And since these are division, I could expand that logarithm by subtraction. Okay, so just like normal, I would do that first before I do any derivatives. Should be a bracket. Yeah, that looks good. And now this 1/2 is being multiplied to everything. Okay, that looks a little bit better because these constants are just going to carry down. So let's go ahead and do the derivative. This 1/2 is just going to carry down. Okay, same with this 1/2. So now when I'm taking the derivative of the natural log of x plus 1, it's just going to be 1 over x plus 1. Chain rule times the derivative inside is just 1, so you don't need to write that. Minus the derivative of the natural log of x minus 1, 1 over x minus 1. Okay, that looks pretty good. Again, that 1/2 is just being multiplied to those ln's. Inverse tangent, this one's the easy one, 1 over 1 plus x squared. And you can do x squared plus 1 if you want to. This is just kind of like the textbook definition of it. Okay, so what I did was first of all, I distributed the 1/2 to everything. So I was like, okay, this would be the same as 1/4 times this one, which I'm going to start making common denominators there. And 1/2 times the arctangent one, like that. Okay, so within here, I'm going to start making common denominators. Which is not too bad. First fraction times the top and bottom by x minus 1. Second fraction, x plus 1. Okay. So I'm just going to go ahead and subtract these. Well, I can write out my work, I guess. You're okay with doing that in your head. Just like subtracting them in one step, that's good. So if you think about this, the only calculus we did was in this step right here. Was knowing to do the derivative. Everything else, pre-calc application in the first step, algebra. All right, now those fractions are ready to combine. So I have x minus x, those cancel. And I have, careful here, -1 minus 1, I would get -2. Those ones do not cancel. Okay, so then I simplified this. I was like, hey, I could make that a 1/2. And then I essentially factored back out the 1/2 and then added these ones together. So maybe we didn't have to necessarily distribute that, but it did help me simplify a little bit. But now I'm going to try to make common denominators with these ones. Okay, so this fraction I'm going to times the top and bottom by 1 plus x squared. Now, obviously, if you were to multiply these out, you get x squared minus 1, right? We get a difference of squares, so we don't have the same denominators right now. And this one, I'm going to times by x plus 1, x minus 1. Okay, everybody with me? A lot of common denominators here. Yep.
Before anything goes too far, the -2 is supposed to be -1.
Thanks. Good catch. You're right. Okay. This is going to be so satisfying when we're done. So that would give me a -1 minus x squared in my first fraction in the numerator. Oh, I see. I brought out a negative. Okay, that's okay. We should still get the same answer. I did a little different on my paper. And then I am going to have to multiply these together, so I'm going to combine like terms. That's a difference of squares, such as x squared minus 1. Almost done. So x squares cancel, negative x squared plus x squared. And I'm getting -2. So those cancel. So a perfectly fine answer to this problem for me would be -1 over that LCD. Now, as I mentioned, you're not assessed on, well, actually, no, you could. This one's inverse tangent. I thought for some reason we did inverse secant. I think that was last one, cosecant. This is a good answer. On a multiple choice style type of problem, they might multiply out the denominators. So if you were to do that here, you obviously get, that's x squared minus 1. So if you multiply those out, you get x to the 4th minus 1. So maybe just, again, recognize this. But I'm okay with you just simplifying to there. Or another answer they could really do, since you have a negative fraction, it could also be written like this, where this is a positive and maybe they have 1 minus x to the 4th. That's another way. Either of those answers say the same thing as yours. Okay. Good stuff. So that's pretty much the new rules for this lesson. Now we'll just do some applications. Oh, classic particle moving along the x-axis. Particle moves along the x-axis, so that's position in feet at any time greater than or equal to 0 is its position function inverse tangent of the time squared, where t is the time in seconds. Find its velocity at any time t. Okay. We know that the velocity is the derivative of the position. So let's go ahead and find the derivative now that we know how to do inverse tangent. Inverse tangent is 1 over 1 plus x squared. So my x in this case is t squared, chain rule, times the derivative of x, or whatever you're taking the inverse tangent of, 2t. My velocity, I would just simplify to 1 plus t to the 4th in your denominator, and bring that 2t up to your numerator, and that's a-okay. This is the velocity at any time. So we can find the velocity at 0. Velocity after 10 seconds. When is a particle at rest?
Velocity equals 0.
When the velocity is 0. Yep. When the velocity is 0. Okay. That's it for that one. Oh, dang it. I thought I did an imdiff one. Oh, I did the next one. Nice. I really want to do the imdiff one. Oh, well, I can always save it for Friday, too. Okay. Find any relative extrema. Ooh, another derivative application. Probably going to have to make a science chart. Using first derivative test. All right. Let's start with finding critical points. So you find the derivative. Which inverse sign? 1 over the square root of 1 minus x squared. This is a very fair AP style question, so that's inverse sine and inverse tangent. Inverse tangent, 1 over 1 plus x squared, and then that 2 would just carry down, so let's go ahead and put that 2 in the numerator. Okay. Now, one thing I want to point out, well, actually, let's go this way first. So when we're finding critical points, remember we got to look at two case scenarios. When the derivative equals 0, where we have horizontal tangents, that's going to help us locate relative maxes and mins. Or where the derivative is undefined. So we'll take care of that in a second. But go ahead and mark that. I always mark it off to my paper so I remember to come back to that. So to find these critical points, if you're given your graphing calculator, we would just use our graphing calculator. If not, we would try to solve this algebraically. This one, I got to a certain point trying it algebraically. So let's say I was trying to do this. I would probably add over this to the other side. And I would probably just like create a proportion here and cross multiply. Honestly. So I would get 1 plus x squared equals 2 square root of 1 minus x squared. And then I would try and square both sides to get rid of that radical. Okay, this squared. Let's see, would give me x to the 4th plus 2x squared plus 1. Over here, when you square this, don't forget to square the 2. And then that square cancels that radical. So you get there. Okay, let's see if we can set this equal to 0 and factor it. So I have x to the 4th plus 6x squared minus 3. So you probably get to this point and you realize, this I can't factor. Because, I mean, it is in quadratic form. It is a trinomial, but there's not two numbers that multiply to 3 and add to 6. So in this case, we have to resort to our graphing calculator. We have to type this into our y1 and look for zeros. So we're seeing when this equals 0. Okay, let's do that quickly. This will be perfect. We'll save the imdiff one for tomorrow. All right, so x to the 4th plus 6x squared minus 3. Whoa. Now, since we're looking for zeros, I want to scale my axis like right so I can just really view the x-axis. All right, now if you're worrying about what you need to set your window to, you're like, what if there's one that's like way bigger? I just did 10 for the x-axis. What if there's one that's way bigger? This is going to go back to the domain of our original function, which we'll talk about in a second here. But let's go ahead while we're in this window. Not intersect, calculate the 0. That's 2. Let's see. Whoa. Look where my y is. It's like way up in the 400s. Come on down. He's just coming. Left bound. Right bound. Guess. 0.68125. There's actually another one. So before I go back to that, let's talk about ones that are possible. So looking at my original function, we have inverse sine and inverse tangent. We talked about this, that the domain for inverse sine, I think sine is the very first one I did. Oh, that's inverse tangent. The domain for inverse sine was only -1 to 1. Okay, so looking at my possible like values here, these are obviously going to have to be fitting within my domain of -1 to 1. So I don't even need to look at any ones bigger, but I was like, ooh, is there anything from -1? So I might adjust my window here. And I'm like, I better look, maybe let's just go -2 to 2. And then I'm like, oh, there's another one. And usually, I kind of tell my students like a good like general rule of thumb is to just kind of set your window at like -10 to 10 just to be safe. But the more you know about the functions and all their properties, the more like you can save yourself time from just guessing and adjusting your window. So we actually have horizontal tangents at both positive and negative 0.68125. Okay. So that's just where we have horizontal tangents, where the derivative is 0. I could also have critical points where my derivative is undefined. So looking here, I see I have 2 denominators that could be 0. You do this one, you realize, oh, that's going to give you imaginary. So look at this one. Square both sides. And I get plus or minus 1. And that's at the exact like endpoints of my possible domain. Okay, so we have undefined values at the endpoint of my domain of my curve here. So here's what my sine chart would look like. It's going to start at -1, and it can't go higher than 1. And then we have these 2 zeros. I'm just going to do this. That -0.61 and then positive 0.61. Now, since this was a question that involved my calculator, obviously, I wouldn't have been able to algebraically solve that. I personally use my calculator to do the sines chart. And what I mean by that is, here's my derivative, or actually, you know what we could do? We could do this. This would be probably even better. We could actually type in our function. So inverse sine, second sine of just x, minus 2 inverse tangent of x. We could make our y2, our red one, graph the derivative instead of having to type in what we got for the derivative. And what if we were wrong? All right, so math 8. I want to take the derivative of my y1 for all x's. And then it'll graph both. So here you can see that domain is only from -1 to 1 of the original, -1 to 1. And then here's my derivative. So use your sines chart here. It's obviously positive between -1 and that 0, and we could have calculated the 0 right on this screen as well if we wanted to. We could have calculated the 0 right away if we knew this was a graphing type of problem. It's obviously positive in between those. This is the first derivative test. F prime is positive. And then it's negative in between the 2 zeros. And then switches back to positive. Okay, we'll finish that. Tomorrow, Friday. Which, yes, I'll have to get 5.8. lesson notes ready then. Come on. Oh yeah.